Hello everyone, welcome to topic 7.4, calculating the equilibrium constant. By the end of this, you should be able to calculate Kc or Kp based off of experimental observations of concentrations or pressures at equilibrium. So in the previous lesson, we learned how to write the equilibrium expression and the reaction quotients. You can calculate the value for these by plugging in experimental concentrations or partial pressures and the coefficients from the balanced reaction. So we have some examples here. And so they show you, given these expressions and the values provided, how we would substitute them in and get either a reaction quotient, or we could even solve, if we know the equilibrium constant, solve for an unknown pressure. Okay. Please note that the equilibrium expression, so equilibrium constant and reaction quotients, have no units for this. So this is going to be some math using the stuff we did in 7.3. Okay, so let's look at some examples. So what is the value for the reaction quotient? Please remember that that is labeled as Q for the following system if we have the partial pressure values below. Okay, so it helps to first write what Q is, and since these are partial pressures, we have to use P. So it's always products over reactants. So our first product is CO2, and that is to the third power, times the other product, which is H2O, so pressure of H2O, to the fourth power, over our reactant, so the pressure of propane, and it's got a coefficient of 1, so we don't have to write it, times the pressure of oxygen to the fifth power. So now that we have a reaction quotient expression, we can substitute in the values given to us and see what Q is. So substituting in for CO2, we have 0.789 atm to the third power times the pressure of water is 0.123 to the atm to the fourth power, all over the pressure of propane times the pressure of oxygen, and the pressure of oxygen is going to be to the fifth power. So now we use a calculator to solve for Q, and you should get 4.64 times 10 to the negative 8. Please remember that Q and K do not have units. Okay, so now we're going to look at another example. The reaction given has an equilibrium constant of 0.0234, so that is K. Given the following concentrations, okay, that tells us it's Kc is this. Find the equilibrium concentration of C. Okay, so we're going to do something similar to what was done up here, but with concentrations. Okay, so our first step is to write our equilibrium expression. So Kc is equal to our products, so the concentration of C squared, and we know it's square brackets for concentration because units are molarity, times the concentration of D, all over the concentration of A squared times the concentration of B. And so it says to solve for C, so C is going to be our X, or our unknown. So that's the one we're going to solve for. So substituting in what we do know, 0.0234 is equal to C squared, because I don't know that one, times D, which was 2.91 molar, all over A squared, so A was 0.261 molar squared, times B, which was 4.13 molar. Okay, so I'm going to simplify this to get what C is. So I'm going to move all of these things. So I'm going to multiply by the bottom, divide by the top, and take the square root of all of it to get C is equal to 0.0476 molar. If this reaction were performed at a lower temperature, where the KEQ is lower, what will happen to the amount of all the reactants and products in terms of increasing or decreasing by X or a multiple of X? So if the equilibrium expression, so KEQ or KC, is lower, the denominator so there would be fewer products and more reactants. Okay, so that concludes 7-4 notes. Please complete the You Do, check your work, and thank you for tuning in.